Thank you very much. Okay, thank you everybody. So welcome to this webinar on Ansys Motion. So I'm going to talk to you today for about 45 minutes on the Ansys Motion product, and then we'll leave some time at the end for a Q&A. So Ansys Motion, what is it? What does it do? What problems does it solve? How does it do it? So Ansys Motion is what we're calling a new paradigm in multi-body dynamics. Before we dive into what that means, we really need to just think about what multi-body dynamics is and why that's important to us. When we think about multi-body dynamics, what we really need to be thinking about here is mechanisms, the study of mechanisms. And whenever we study a mechanism or think about a mechanism, the kinematics of that mechanism are going to be important. And they're important because when a mechanism is moving, the locations of maximum stress and the locations where fatigue might occur change due to the movement of that machine. And multi-body dynamics at a very simple level can give us insight into this. Really perfect example on your screen here of a crane. When you look at a static situation or a static solution, you predict a region of maximum stress. Look at that in a dynamic context, though, that region of max stress can change. Suddenly, you need to be focusing your design attention onto a completely different area that was only revealed by doing a kinematic analysis. And what you see on screen here is a very simple linear case. What if it was much more complicated? What if there were large deformations, large rotations, high frequency contact involved, or plasticity, or even very long transients? And that really is the sweet spot, I suppose, for the Ansys Motion product. What is Ansys Motion? Ansys Motion is a dedicated standalone multi-body dynamics tool. So it's a software suite in its own right with its own pre-processor, post-processor and solver, and an integration into Ansys Mechanical via an ACT app. We call it a third generation solver because although this is a new product, it has some real pedigree behind it. So this is a partnership product between Ansys and a company in Seoul in South Korea called Virtual Motion. That company is run by a man called Professor Daesung Bae. So if any of you know anything about the world of multi-body dynamics, you may know of Professor Bae already, or indeed of the products that he's created in the past. So in the 1980s, he was instrumental in the creation of the DADS tool. In the 2000s, he was instrumental in the creation of a company called Function Bay, who created a tool that's now called Recordine. And in the 2000s, he created Virtual Motion and combined all of his lifetime's worth of knowledge into this third generation solver, which is now available as Ansys Motion. So Ansys Motion is, like I said, a standalone product. It doesn't need any other Ansys licenses to run, although it does interoperate with other Ansys products. But it is a standalone product that is Ansys Motion. That gives you the pre, the post, and the solve. And then it is 4 toolkits that augment that main product. So they are add-on toolkits that give you extra functionality. So that main Ansys Motion product, like I said, it is a complete solver suite in its own right. It enables you to do multi-body dynamics. The key thing here, though, is it enables you to do it with flexibility included. So you can declare parts to be rigid or flexible, and those flexible parts can even have non-linear material data associated with them, and they can go plastic. It's got this series of toolkits, like I said. So there is a links toolkit. Looks at tessellated repeating sections, whether that's a toothed rubber belt, a drive chain, like you see on the screen there, or indeed caterpillar tracks underneath a piece of construction equipment. They're all categorized as links as far as we're concerned, and the links toolkit gives you a solution for those. The Drivetrain toolkit, that gives you a complete solution for gear train design and analysis of drivetrains. So the ability to create the drivetrains, the bearings, the gears, the shafts, to assemble them all together, to set the contact up between them, to synchronize them, to drive them, and then to look at the kinematics of what you get out. The toolkit gives you a vehicle kinematics and compliance and ride and handling capability. So if you're familiar with something like Adam's car, for instance, the car module within Ansys Motion does the same kind of analysis. And then an easy flex toolkit. So this is effectively a mesh-free flexibility capability inside Ansys Motion. Declare parts as flexible, but you do not need to sit there and put a mesh on them to look at that flexibility. You can do it in a completely automated mesh-free manner. What benefits do you get from Ansys Motion, and what does it do that's sort of different from either other tools that we have or other tools out there in the competitive landscape? Well, first of all, this is the most advanced multi-body dynamic solver that is commercially available today. It is the product of a lifetime's work inside of the world of multi-body dynamics, and it contains some really quite revolutionary solver schemes and methods of doing things within it. It's got this unique, highly advanced, fully implicit solver scheme that doesn't use any explicit solver technology. It's fully implicit, and it is extremely fast. As we'll see in a minute, with some benchmark data, it generally blows other products away in terms of its solver speed. And also, because it is a fully implicit method, it is a highly stable and highly accurate way of solving these multi-body systems. The other real unique thing about it is that it has these rigid and flexible components tied together in one solver. So if you want to model flexibility, there's no need to co-simulate. There's no need to think about data transfer between different solver modules. It is the same solver, and all of that data transfer is handled for you. The super matrix solver that it uses is extremely good at large degree of freedom systems. So very large models, very long transients. It's extremely capable at handling. Contact is also very nice to work with. It uses the same contact algorithms and logic for both the rigid and the flexible material or parts. So whether you're using NURBS from the geometry or whether you're using faceted representations of contact from a meshed part, doesn't matter as far as the contact is concerned. It treats both the same. It also has different flexible solver schemes within it. So it has a nodal finite element solver scheme, and it has a modal solver scheme. So dependent on levels of deformation and levels of contact, you can choose which of those schemes to use. And we'll talk more about that in a little bit. And it's very flexible in the way it interfaces. Interfaces with other software through either its own user subroutine architecture, through functional mockup interfaces, so it can act as a slave within a functional mockup interface, or through a Matlab interface. So you can plug it directly into Matlab and Simulink as well for control system side of things. It's very good at looking at kinematic analysis of any general purpose mechanical system, but with the toolkits, obviously it's got a bent towards vehicle dynamics, drivetrain analysis, and links, whether that be caterpillar tracks or drive belts. It can do plasticity. It's very good at large deformation. It's very capable at high speed frequency contact. So high speed rotating contact is easy to do. So really a whole range of massive benefits that sort of separate it from other tools that are available. Really just sort of to summarize that rather wordy last slide. It is third generation solver. It is the most advanced commercially available multi-body dynamics tool. Very, very capable and high frequency capable contact between rigid and flexible parts. And those rigid and flexible parts can be easily switched between each other at any given point. So you can simply switch a part from rigid to flexible very, very easily with just a click of a button. And because we can look at nonlinear material properties, we can start to look at large deformation problems in the time domain. And you can see some benchmark data down at the bottom there. So some of those are rigid to rigid, some of those are rigid to flexible contact, some of those are large deformation type cases and plasticity type cases. And you can see in each case when we benchmark motion against the competition for these kind of complex contact, long transient situations, it really does blow everything else out of the water. This is really a dedicated high-end tool. We have a rigid body dynamics capability built into the Ansys Mechanical Enterprise tool, and that is very, very capable at doing what it does. But this tool really takes things to the next level. That you can declare rigid and flexible and switch between them and involve them in contact and nonlinearities so easily really sort of raises it up to a higher level. What do you get with Ansys Motion? Well, when you buy the Ansys Motion license, you get access to the dedicated Ansys Motion pre-processing system. You get access, of course, to the full solver, and you get access to the dedicated Ansys Motion post-processing system. That is a general purpose pre-processor and a general purpose post-processor. You also get an integration into Ansys Mechanical. So imminently to appear on the customer portal, hopefully today, maybe tomorrow, there should be an app that will integrate this Ansys Motion product into the Ansys Mechanical user interface for pre-processing. And that's a collaboration between ourselves and between the team at Virtual Motion. So that app will be compatible with 2019 R3 and beyond, and that gives you a new analysis system in terms of the workbench environment you can drop in called Ansys Motion, and you can then use all of the standard Ansys Mechanical pre-processing to set up your model. So standard geometry, material assignment, connections, so you can use the automated contact generation, and you can use the automated joint creation tool inside of there to create the joints and contacts for your model. You can mesh parts that you wish to be flexible, and you can switch flexibility under the geometry section as you can in a normal Ansys Mechanical environment. Then you have a specialized Ansys Motion system down at the bottom, which gives us access to this toolbar up at the top here, which gives you a load of Ansys Motion specific commands and boundaries and functions that we can apply. If we just take a look at that toolbar in a little bit more detail, you can see some of the things that we can do up there. So what we've tried to implement with the Ansys Motion ACT app is to really combine the best of both Ansys Mechanical in terms of its ease of use and its flexibility, but also the standalone Ansys Motion product and some of the concepts and ways that it does things. And once you start using Ansys Motion, you'll realize a lot of its power comes from the fact that it is driven in a large part by functional expressions. We apply equations, functional expressions to drive our boundary conditions and to drive the model. And those expressions can depend on other expressions and call on things like time or displacement of given locations or given markers inside of your system. That gives you the capability to set up highly automated, functionally driven multi-body dynamics tools using standard Ansys Mechanical contacts and joints. Those can then be modified by these additional options that we can apply here inside of the Motion environment, such as altering contact properties if we need to, applying joint load and joint friction commands to the model, applying springs and dampers and making those properties be able to be dependent on functions, which you can define up here. So whether they're functional expressions, step functions, splines, or equations. Also access to co-simulation and import and export of files. And then once you have the model set up, solved inside of Ansys Mechanical, you can at the moment do limited post-processing inside Mechanical. You can play the animation, you can look at displacements, but if you want to do proper post-processing and complete the post-processing for your model, you have the option to click the Run Post-Processor button. That will launch the standalone Ansys Motion post system, pass all the results to it, and display them to you there inside the dedicated Motion post-processor. So if we just look at sort of some of the kinds of examples that we could do with Ansys Motion, I mean, whenever you think multi-body dynamics tools, locks and locking mechanisms always seem to come up, and this presentation is no exception. So you can see here an example of an automotive door latching system, solved there and displayed inside the standalone motion system. And in this case, looking at the sealing force generated on the rubber seals going around the door, and also, of course, the kinematics of the lock itself. We've just been talking about Ansys Mechanical, so we can now run that exact same kind of setup and model directly inside of the mechanical system, and you can see there an output of the fully rigid result we get from that model. But being Ansys Motion, the whole benefit of the system is that we can, in a one click, change a part from flexible to rigid, or vice versa. So in this case, the call, if you like, the claw that does the locking engagement, we can very easily simply change rigid to flexible under the geometry section in mechanical, and we can then run that as a fully flexible, meshed, finite element solved component. And that is really what separates Motion from other things out there and other capabilities we at Ansys have. To give you some idea of timings, to solve that model as a fully rigid system takes a few seconds. Solve that model with a flexible call inside of there takes just a few minutes. It's an extremely fast processor. Another very nice example here, looking at a CV joint. So a high-speed rotating ball bearing system. You've got an outer raceway and an inner raceway attached to a shaft. You've got a series of rigid balls, and then you've got a housing that holds those balls in place, or a cage, if you like. And that cage, in this case, you can see here, is modeled as a flexible system. So we have a full finite element mesh applied to that cage. We can apply rigid body motion to the drive shafts. We can rotate that CV joint up to working velocity. So a pretty long transient run. In this case, a simulation running over several seconds of real time. And we can solve that in Motion within a few minutes to an hour for a solution like this. This is actually a particular a real world customer case we're showing here. They were having problems with the fatiguing and cracking of this cage. And this was something that they hadn't really predicted in the simulations and studies that they'd done before this particular product was released. They then started having warranty issues and these things being sent back with cracks inside of the raceway. Well, at that point, a solution inside of Motion very quickly identifies where these cracks or high stress regions are. Motion has a fatigue solution inside of it as well, as we'll see in a minute. And that enables you to locate these high stress regions, locate the high fatigue regions, redesign some geometry, and then completely minimize them, as you can see over on the right hand side there. How does it do this? Well, it does this through effectively having a whole series of different solver schemes all tied into one solver mechanism. So inside Motion, we have a full finite element solver. So you have the ability to take a part, to put a mesh on that part, and to solve it. So this is not a finite element solver that we would generally use for fully static cases. It's a finite element solver that we can use to mesh bodies inside of our assemblies and solve the finite element stress field and deformation field at the same time as we solve the multi-body dynamic system. There's a very nice example on the right there of an assembly process which includes flexible parts, rigid parts, and the flexible parts have nonlinear material data inside of them and can undergo plasticity and permanent deformation during the movement of that mechanism. So it is an FE solver built into Ansys Motion. An eigenvalue solver. So we can do modal analysis, again, directly inside of Motion. We can pull out natural frequencies. It opens a very exciting door into the world of NVH, noise, vibration, and harshness, and how we can start to look at things like acoustic performance of bits of equipment due to their vibratory effects. So an eigenvalue and modal solver built into Motion. It is, of course, a multi-body dynamics solver, capable of complex contact, capable of doing vibration, but also capable of doing fatigue and damage. So if you feed it with fatigue curves for your materials, you can start to do fatigue plots on your multi-body systems and start to look at where high fatigue locations are, and therefore where cracking and wearing might be worse. It's also a thermal solver. We don't want to miss that out. It has a full thermal conduction capability. You can generate heat, you can conduct heat away. So mechanisms that involve substantial amounts of heat generation can also be simulated by motion. Just to summarize what's available in there, it is a modal solver. So the ability to do vibrational analysis, natural frequency, to look at resonance of flexible parts. It is also a nodal solver, so a finite element implicit system allowing you to look at detailed stresses and strains inside of your components. It is an eigenvalue solver. It is a mesh-free solver if you take the EasyFlex toolkit. All of these different solver schemes have different fidelities when it comes to how they can deal with contacts and nonlinearities and large degree of freedom type systems. Let's take a look at the toolkits that go with that Ansys Motion product. First of all, let's talk about the Drivetrain toolkit. So the Drivetrain toolkit gives us the capability to start to look at complex powertrain systems. And those systems can be rigid, or, of course, being Ansys Motion, any one of those components in there can be chosen to be flexible for any point of the analysis. So this example you see on screen here is an automotive synchronizer. So looking at a shifting system, you can see there with the carrier arm moving backwards and forwards. And this has been set up with the Motion Drivetrain toolkit. So as you'll see here, the toolkit really consists of 4 separate components. It consists of a shaft design area, a housing design area, a bearing design area, and a gear design area. And each of those allows you to either import geometry from CAD or create your own geometry directly inside of the Motion preprocessor system and define how it will be used either as a shaft, a housing, a bearing, or a gear. So gears first. So the gear system, effectively what you are doing in here is you are at the first stage using a 2D parametric representation of a gear that you have loaded in from a catalog of predefined gear types. And you are then customizing that gear in terms of its size, its dimensions, the number of teeth. Then zooming in an extra level of detail onto the individual profile of the teeth themselves, where you can then make micron-sized adjustments to the tip and the crown profile of your teeth to change how they intimately mesh and link with the teeth on the next gear. Then you can output gear stiffnesses directly inside of the preprocessor, and you can then put that gear to one side until you've got a shaft and an assembly that you're ready to use that gear on. So you can create spur gears, helical gears, planetary, rack and pinion, cycloids, worm and wheels. There's templates for all of these gear types in there. Then you can go in and in detail modify the profile, slope and crown, tip relief and everything like that. Then you can start to add things like misalignments and imperfections, and then go on and assemble those gears together into the overall system. So once you've done the gears, you do the same with the bearings. So again, the bearings, you're presented with a 2D representation of a bearing with a parameterized series of dimensions that you can control and change, or you can load those bearings in directly, again, from manufacturers' catalogs. So the major bearing manufacturers like NSK, SKF, Koyo, and FAG are all represented inside of Ansys Motion, where you can simply pick up the bearing via a part number and load that bearing in, customize it if you wish, and then go on and assemble it into your model. Again, once you've built the bearing in 2D, you can immediately in the preprocessor pull out stiffness of that bearing and a full orthotropic stiffness model that you can go on and use in a simplified model if you wish to. The shaft and the housing, much less complicated generally. The shafts you can create directly in Motion by putting in numerous defined sections via this input that you see at the top right, or you can load in from CAD. Similarly with the housing model, you can load that in from CAD, or you can create simple housings inside of the Motion system, but housings do tend to be more complicated and want to come from a CAD source. Maybe worth mentioning at this point that Motion does also, of course, integrate with SpaceClaim. So if you buy Ansys Motion, you get a SpaceClaim integration, and you can push models from SpaceClaim directly across to Motion. So let's just look at another example of the Drivetrain toolkit, and you can see here an example of an integrated motor and reduction gear system, what might be known as an e-axle from an electric vehicle. In this example, what we're going to look at here is a double stage reduction sort of linear gearbox type system. And we've been using the Drivetrain toolkit in order to represent the major parts here of the drivetrain side of things. So not the internals of the motor, but the drivetrain itself. So the gear sets, the ball bearings, the housing. Then we can increase and drive that system over the range of operational speeds that we expect it to run at, and look at the sort of outputs we get from this system. So a couple of the obvious things we'd want to be looking at. Firstly is the intimate design of the gears and the gear teeth themselves. The ability in a loaded condition with flexibility of the shaft and flexibility of the housing represented to look at the detailed plots of pressure you get on the teeth inside of that inside of that drivetrain, inside of the gears. Ensure those pressures are as uniform as possible, as symmetric and centered as possible. But then also to start to look at the noise, vibration and harshness that come out of this. So, there's a combination of outputs from the gear mesh frequency and the motor frequency. And we can plot that directly inside of Motion in terms of these waterfall diagrams like you see down at the bottom left there, where we can then really start to pick up on where the high noise regions are inside of that operating envelope and what's causing those high noise regions. Is it from the gear mesh frequencies? Is it from the driving speed of the motor itself? So really, just to summarize the Drivetrain toolkit, multiple stages. We create the shafts or load them in. We create the bearings. We create the gears or load them in from CAD. It's always another option here. We assemble them all together. We drive the system with a given input, with a given function, and we can look at the detailed kinematics of what goes on inside of that gear train. Okay, so next, let's talk about the links toolkit. So the links toolkit gives us, as I said earlier, the ability to model things like chains and belts, and as you see on screen here, things like caterpillar tracks inside of vehicles. So it's again a toolkit that gives you a way of easily setting up these tessellated patterned segments to connect them together, like you see on screen here, to assemble them, to make them with a driving sprocket, to make them with rollers or tensioners that are there inside of the assembly, and then to solve that whole belt drive, chain drive, track drive, whatever it may be. Being Motion, we can choose what level of fidelity we want to dive into. We can look at this in a fully rigid manner. We can look at this in a fully flexible manner, or anywhere in between in the time domain over a long transient simulation. So to see an example of that links toolkit in use. So here a piece of construction equipment moving along what's known as a rough road test. So this is a real physical test that is carried out on bits of equipment like this, where they drive them along a concrete road with a series of effectively rigid metal cubes or rectangles embedded into the surface. And as the vehicle drives over them, obviously large stresses are imparted on the caterpillar track system. And what you really don't want is those caterpillar tracks to shed or to come off. This again is actually a customer example where the customer in this case was finding that they were getting shedding of these tracks. Caterpillar tracks that were supposed to last 10,000 hours were coming off after just a couple of thousand. And that was actually due to excessive wear they were getting due to the interface with the sprocket. So again, nice example of being able to use the multi-body dynamics tool to pick up on this. The tool they had been using before, when they did the design of this bit of equipment, simply hadn't had the nonlinear capabilities to be able to model the flexibility of those links, and therefore didn't catch the fact that they could shed when there were certain size blocks met at a certain angle at a certain driving velocity. So the links toolkit here, is invaluable because you can imagine setting up these repeating track sections. You need thousands of contact pairs. In this case, something like 1,300 contact pairs were automatically created. The joints between the tracks are created. The physical geometry is mated correctly, such that the sprockets and the tracks actually mate together in the right way at time 0. And then you can go on and drive the system forward. So another example, the one we saw in the sort of little thumbnail earlier on in the presentation, looking at a bicycle drivetrain and a gear change system. So the derailleur system, you'll see the chain here slip onto the purple or pink sprocket there. And you can see or imagine that, contact like that, it's a difficult contact to pick up. You need to be able to model the friction inside of the links, inside of the joints between the chain sections, but also the friction on the sprocket itself. And you can see when this contact happens, it's a very jarring, very irregular contact. You can, nice and easily pick up with motion. And finally, the car toolkit, or penultimately rather, the car toolkit. So the Ansys Motion car toolkit gives us a capability for looking at vehicle kinematics and compliance and vehicle ride and handling type situations. So things like toe angle tests and lateral displacement tests, and really a complete vehicle kinematics solution. So as I said earlier, if you are familiar with solutions on the market already, things like Adam's car, then Ansys Motion car toolkit you find does very much the same kind of things. So it comes pre-armed, if you like, or preloaded with a whole series of templates and subsystems to enable you to very quickly and easily set up these kind of complete vehicle or half vehicle type models. That's representing the suspension system, the springs, the tires, and the steering system. And again, this toolkit gives you the ability to plug into catalogs of tire types. So with Ansys Motion, you can plug into standard tire models. Things like Swift tire and F tire models can be integrated into Motion to represent the tire tarmac interface and the stiffness and torsional and lateral stiffness of your tires themselves. So if you are familiar with vehicle ride and handling and kinematics and compliance analyses, then all of these kind of inputs and outputs should mean something to you. So things like fishhook tests and double lane change tests are all standard vehicle kinematics tests that are applied by the automotive industry. And the Motion Car Toolkit, you can see here, has kind of predefined, pre-created templates where you can input this standardized data and plug it in. Of course, being Motion, again, if we want to dive deeper, if we wanted to, let's say, start to look at the flexibility and stresses generated one of the suspension arms during the simulation, that's no problem. Because of the flexibility of how we can switch rigid to flexible and flexible to rigid, we simply pick that component, switch it to be flexible, solve the model, and we could look at the stresses inside of parts at the same time as we're looking at the multi-body. So again, often removing the need for what traditionally would be viewed as two separate simulations, multi-body and one for the detailed finite element. Well, in Motion, you can do those together at once. And then finally, the EasyFlex toolkit. So the EasyFlex toolkit gives you a mesh-free flexibility capability inside Motion. If you think, well, why is that useful? Well, if you're sitting there listening to this call and you are a dedicated multi-body dynamics user, then it may well be the case that you are simply not familiar with mesh generation. If you drive multi-body tools every day, you're generally looking at fully rigid mechanisms, and flexibility is something that is either passed to the stress group or is done afterwards with another tool, or even maybe co-simulation, but with a separate tool at the same time that someone else can drive. So with the EasyFlex toolkit, it gives you an ability to represent flexible parts and flexible components and take account of that flexibility in a mechanism without having to do any mesh generation at all. So if you're familiar with the sort of technology that's available in something like Ansys Discovery Live, this is a very similar way of doing things. It's a sort of behind the scenes, a Cartesian voxelization scheme that automatically breaks the geometry up into a series of voxels and solves the stress and deformation state on those voxels. You control it simply with a slider that, normally in these kind of schemes, and same in Motion, really sort of goes from accurate and slow to less accurate but fast. And you choose your fidelity at a scale between 1 and 5, and you get a flexible stress field and deformation field in your parts. A very nice capability, particularly if you're dealing with complex geometry, something like this car chassis. You can imagine meshing that. Even if you're good at meshing, I would hesitate at diving in and meshing a geometry like that to be used in the multi-body simulation. Whereas with the EasyFlex toolkit, nice and easy. So if we take an example, this is another nice example of where EasyFlex is good. This is a vibro hammer that you might hammer piles into the ground with. So you've got a drive shaft coming in. You've got a couple of bearings. You've got a clamping system. You've got an engagement system, and you've got an off-center spinning weight or mass that gives you the vibration. So modeling all of that in terms of combination of rigid and flexible components is something that Motion does really nicely. But you can imagine this outer casing shown here in pink and white and pink and green and red. It's a very complex shape. It's got lots of webs. It's got thin sections. It's got thick sections. It's got holes. Putting a mesh on that, even for an experienced mesh user in Ansys Mechanical, could be a non-trivial thing. Whereas if you've got the EasyFlex toolkit, blink of the eye and you're up and running. And you can see that example sort of playing out in an animation form on screen here. So you saw a clamping stage to begin with, then you see that red off-center mass spinning around extremely quickly and providing us the vibration. And all of that stress field and flexibility you see there, no mesh involved at all done with the EasyFlex toolkit. And then one last example I really just wanted to talk about is a sort of nice show here of a combination of the EasyFlex toolkit and co-simulation with other tools using the functional mock-up interface. It's a little mini loader. It's driven forward, and we're looking at the loads and stresses and deformation in these lifting arms when we pick up this defined series of weights sitting on the floor. Using the EasyFlex toolkit, we can easily set those parts to be flexible, and we can look at the kinematics and forces generated in all of these joints and hydraulic struts during the movement. But nice thing about Motion is you can co-simulate with other tools. In this case, co-simulation with a hydraulics analysis package. The obvious thing here is you want to know okay, this is the weight I need to pick up. This is how I want the kinematics of the bucket to move. This is the speed I want it to move at. What power needs to be supplied by my hydraulic pump to the hydraulic system to achieve that kinematics? Well, in order to answer that, you need to solve the hydraulics and the kinematics together in one. And that's what co-simulation enables us to do. So there's two ways to co-simulate with motion. You can co-simulate using the standard functional mock-up interface. Ansys Motion acts as a slave inside a functional mock-up interface and will provide functional mock-up units into that interface to allow you to pass data two-way into motion and out of motion into your other tool. It also plugs in to Matlab and Simulink. So there is a Matlab interface built into the standalone motion pre and post processing systems. And that allows you to, again, directly two-way communicate with Matlab and with control systems that you might have in something like Simulink. Or if we're talking in Ansys language, things like Simplora, again, through functional mock-up interfaces. Thank you for your time. Really just some conclusions from what I've said today. So Ansys Motion, it's a new partnership product into the Ansys portfolio. It's a partnership between us and the virtual motion company created by Professor Bay. It is a third generation multi-body dynamics tool with an extremely advanced and unique solver scheme that it uses. Really the culmination of a lifetime's work in the world of multi-body dynamics, and offers something that really does set it apart from the competition. So just to summarize in kind of 5 points, it is a single solver scheme for rigid and flexible modeling. So you have nodal meshed finite element solvers, you have modal analysis solvers and eigenvalue solvers, you have rigid parts, and you have these mesh-free easy flex parts, all available in a single tightly coupled solver scheme. No co-simulation needed between them, no thought about data transfer frequencies or size of data packages or anything like that. It's all handled by the solver. It's got a very capable contact scheme. It can pick up extremely high frequency contact over very long transients without severely extending the runtime of the simulation. And that contact can be applied to both rigid and flexible bodies. And again, that's something that really sets it apart. Because the flexible solver is built in, you can have flexible parts involved in mechanisms and be involved in contact inside one single model. And the sort of state-of-the-art solver that it uses is extremely fast. I've myself done quite a lot of benchmarking of this product between both our own implicit and explicit solver schemes and competitor solvers. And every single time I've tested it, it's surprised me at the speed of this Ansys Motion solver. It is unreally quick. And finally, you know, it's functional and flexible. It has its own user subroutine capabilities to enable you to customize it. It can plug into Matlab and Simulink, and it plugs in to other bits of software through the standard functional mock-up system.